So, hi and welcome everybody to the lecture titled Polar Codes for Error Control Coding. This is a lecture which is part of a series of lessons on 5G technologies used in the future wireless networks. And in today's lecture, we will continue from where we left off from the previous lectures where we talked about introduction to error control coding. We explained convolutional coding, block coding, and how to encode your message properly in such a way that you can receive it reliably with minimal number of errors. Now, we know that convolutional codes and block codes and all the other codes are really very conventional basic types of codes that were used in the old systems. And with the advances in technology and the emergence of new generations, we are now trying to come up with new types of codes that are not just able to achieve very good reliable performance and improve the bit error rate and the data rate simultaneously, but also reduce the complexity of the overall system because devices are gradually becoming less complex, like Internet of Things devices you are talking about. And the second point is to make these codes work even for short block length. For example, for the cases where you are trying to serve ultra reliable low latency communication, you need the code to give you the expected performance even when it's operating over a short length code, and not just the case where you have very lengthy codes so that you get the optimal performance. So motivated by this, the researchers they have conducted several studies and research on this domain, and they came up with a concept called polar codes. So what's polar code? What's polar coding and the features of polar coding? So this is what we are going to know and explain in this lecture. So the agenda and the outline is going to be structured as follows. We will talk about the coding problem, briefly introduce it again, remind you of the coding problem, although we discussed it before, but just for the ones who are attending this for the first time. And then we give you a brief introduction to polar codes, the mastermind behind polar codes, and then the code construction, the encoding process, the decoding process, give you some simulation results, and share with you some codes that you can use in the future in order to build on top of your polar codes. You know, you can, whatever your algorithm is, whatever your system design, or you are basically working at the physical layer. So if you come up with a technique that can improve the performance, you can eventually improve it more by integrating your algorithm with polar codes. So you just put encoding and decoding and make it coexist with your code, and your performance will get better, hopefully. So we also, this is also another goal for us to be able to integrate the MATLAB codes of polar coding with the existing MATLAB codes you have related to your algorithm or system. So the coding problem, we said before that the coding problem is all about trying to encode your information bits to another sequence of bits that we call it the code word sequence, or the coded sequence, in such a way that this coded sequence you can receive it and decode and use it to decode your message information reliably. And you can do this by introducing some intelligence to your system. This intelligence is basically in the encoding and decoding process. So initially, for a system which is uncoded, what do? You just take the k bits and map them to and send them directly through the channel, and you receive another sequence of k bits which are noisy, affected by the channel. And this would be very difficult for you to recover the originally transmitted bits because they are corrupted and manipulated by the noise. Now, to overcome this problem, you need to add some redundancy and introduce some intelligence in the encoding process in such a way that this intelligence enables you to detect and correct the errors caused by the channel at the receiver side and then recover your message bits successfully. So this was the main motivation and main goal of coding. But what's the problem? And coding, we always aim and try our best to achieve the Shannon capacity. We try to come up with codes that can achieve Shannon capacity. What's Shannon capacity? Each noisy channel has certain capacity, certain data rate that it can allow you to transmit over it due to limitations by noise and the environment. So our goal is to approach that capacity, be very close to that capacity, as close as possible, while also achieving very good reliability and very amazing and very acceptable data rate, which is almost close to the capacity. So here, this is the blue line is the line that shows that Shannon capacity. And Shannon capacity is the maximum rate you can transmit over a noisy channel or a noisy that's affected by some impairments due to maybe not only noise, fading or really fading or whatever. So here the blue, we have the x-axis here, EB over N naught, which is the signal to noise ratio at the receiver side, the power of the received signal over the noise. And on the y-axis, you have the spectral efficiency. The spectral efficiency is basically the amount of the maximum number of bits or data bits you can transmit given the resources of the channel you have. Let's say you have 100 time slot, 100 subcarriers. Within these 100 subcarriers or 100 time slots or 100 antennas, how many bits you can transmit? The more the better. And we usually, before we try to design our systems, we don't know the capacity. That's why we need to have a reference, a threshold, where we know that this is the maximum that theoretically can be achieved. And we try by our designs to approach that theoretical findings. Yes, the theoretician, the mathematician, they come and they try to analyze this channel. What's the channel at the end of the day? The channel is a statistical function, yes, probability function. So you try to, for certain input, there is the output is affected by the characteristics of the channel, which are usually random and statistical, and you try to find the capacity of this system. And mathematically, you say if your input is uniform and your channel is Gaussianly distributed, then the maximum data rate you can transmit is this value, this function. And you put this value. Then the designers, after that, the engineers come and they try, the theoretician have put the limit for you, they have defined it for you, they found that this is the maximum you can achieve. But the mathematicians, they don't know how to achieve that. They found what's the maximum you can achieve, but they don't know how to achieve that. So your goal is to come up here and try to invent algorithms and techniques and designs that can really approach the value that the mathematicians found or the researchers before you. And you cannot achieve that by just guessing. You need to bring to the table a new intelligent design that has some intelligence in it and that can make sense, and you utilize the characteristics of the function in such a way that you achieve that limit. And unfortunately, the surprising news that I want to tell you, since 1949, yes, this is the 1948, which is the time that Shannon defined the term bit. Yes, the term bit was coined by Shannon in 1948. and he studied the capacity of the capacity of noisy channels, yes, and found that the capacity is this much, and then he set the limit, the capacity limit, and then gave the engineers after that and the researchers guidelines that this is what you can achieve as a maximum capacity for your channel. Then since that time up until recently, there were no code invented in this period of time that was proven to achieve the capacity of Shannon in a mathematically derived way. So how in 2000 until 2009, a paper called Polar Coding, Channel Polarization by Professor Erdal Arikan was introduced, and in that paper they explained the fundamental functionality of polar codes that was proven to achieve the capacity that Shannon talked about it 60, 70 years ago. And this was really very great news to the academia, to the researchers, to the industry, that this is the first provably achieving capacity codes, and also you can achieve that with low complexity and with not much overhead, and that's why it made it very attractive to the 5G technologies. And therefore this coding, polar coding, is one of the codes that was introduced and accepted in the 3GPP standardization, and soon is going to be used and implemented in most of 5G phones. And it's basically going to be used with the control channels. So now, due to this, we are learning polar codes. We want to know what this polar codes system, how does it work, what are the key elements of it, the key factors affecting its implementation, and whether we can improve it more in the future. So the polar coding system originally proposed for binary input, discrete memoryless channel, discrete memoryless symmetric channel, and it includes 3 steps: the encoding process, the decoding, and then the code construction. And here is the first paper on, it's not the first paper, but it was the paper that explained everything related to polar codes and to the phenomena called channel polarization. The polar code design was inspired by the deep understanding of how the channel, the noisy channel, affects your transmitted bits, because really you can only come up with groundbreaking, amazing technologies only when you have full, deep, fundamental understanding of the problem and how things work and how are they related to each other. And this is what happened for polar code case. The author first understood how the noisy channel affects the bits, the transmitted bits, and from that deep understanding, he was able to come up with coding scheme that can achieve almost the capacity found by Shannon theoretically, and then implement an easy encoding and decoding structure that enables implementing and achieving the desired performance in terms of reliability and data rate with minimal complexity and latency, which made it very stunning and very appealing to the researchers and from both academia and industry. So here we go. This is the inventor, Professor Erdal Arikan from Bilkent University, Ankara, Turkey. He was born in 1958 after 10 years from Shannon's paper on channel capacity, noisy channel capacity. and he's well known for as the inventor of polar codes. He received many awards and many recognitions for his achievement, and also he was awarded officially by the founder and CEO of Huawei, not only IEEE and these academia people, but also with the founder of Huawei, because Huawei is the company that was pushing for polar codes, and they wrote so many patents related to how to implement it and how to use it, and they introduced it in the 3GPP meetings, and it got approved, and they are going from now on use it for control channels, which are more important than the control channels usually are more important than the data channels, because the control channels are the channels responsible for driving the data and giving the information needed in order to be able to recover your data successfully. So the most outstanding paper reporting original work in any of the IEEE transaction journal, magazine, or proceeding. So it's such a remarkable point in history of wireless industry and information theory and communication theory. It's a great achievement, and it's really one of the few key inventions that got accepted by the 3GPP standardization. So now let's go and talk in a more technical way about the polar codes and the basic fundamental features that they have, which is called channel polarization. What's channel polarization? Before we talk about channel polarization, I want to explain to you why I got interested in this polar codes. Although I am a little bit not too much interested in coding. Usually I am interested in modulation, inventing or coming up, designing new modulation schemes at the transmitter, new multiple access schemes, new security schemes. But I don't have too much interest in polar codes. But when I heard, while I was in my graduate studies, we had a course on error control coding, and this was out of the course, polar codes, because at that time it was something new, not yet well known it's still in the research phase. So my task, my project was something like understanding these polar codes, and we try to see how it works. I like usually it's better always to work on something relative to the literature. So you work on the topics that are hot, that are attractive, that are expected to be having very high impact in the community and in the globe. So I got this topic and started investigating it by my own. There was not too much material on that, and I found when I got the topic and I wanted to work, I just didn't like it from the beginning. What's polar code? I never heard of it. I don't know what's it, why, and I don't have any desire to get into that domain. But once I reached to this channel polarization, I say, wow, this is the thing that we have been always doing for the channels, the wireless channels, when we are designing our data. And when we transmit our symbols, we usually, once we measure the frequency selective fading channel, we say that there are good channels and bad channels. And in one of my papers, I said that these bad channels are the bad ones that we should not transmit over them. And also there are many other papers as well. But this was implemented on the symbol level after modulation. You understand me? Not on the bit level, not in the encoding level, on the symbol level. So we were saying in these papers that these bad channels are the ones that are limiting our performance. To explain this more, let me give you just how important this feature is. So let's take the example. When you have a wireless channel like this, and you basically want to transmit your data reliably. If you transmit, this is your data packet. If you transmit your data packet, these are the symbols, yes, symbol 1, symbol 2, symbol until symbol SN. When you transmit this symbol over this channel, most probably you are gonna receive your data successfully because this channel has good gain. Since it has good gain, then the channel acts like a power amplifier. It amplifies your signal because you can treat the channel at the end of the day as a filter. But now when you transmit your data here over this back channel right there, you will not, most probably you will not be able to recover your data successfully because the channel suppressed, we call the channel suppressed your data at that carrier to a level that it has become below the noise, and the receiver does not see anything except noise. And how are you gonna get your data from noise? The data is below the noise level, and that's why you get errors here. You never detect your bits correctly here. And I investigated this problem during my studies and found out that this is really these sub-channels are really very bad, and these are the ones responsible for limiting our reliability performance. So if we just try to avoid them, we don't transmit over them whatsoever, and use these subcarriers in order to do some other functionalities, because at the end of the day, these subcarriers corresponding to these subchannels, they are occupying some bandwidth. We don't want to lose them. Yes, I don't want to transmit data over them, because if I do, I will lose that data. I will not be able to recover it correctly. But at the same time, I want also to be able to make use of it. I don't want to lose it. Yes, that was the mentality. So what I did, we utilized the subcarriers corresponding to low subchannel gains. We utilize them for other functionalities like reducing the out-of-band emission of OFDM. Yes, I told you OFDM has large side loops, and these large side loops can introduce significant interference to the adjacent symbols or adjacent users. And also the peak to average power ratio of OFDM, if you remember with me from the previous lectures. So if I cannot use them for data, because if I transmit, I will lose the data, then why don't I use them for also other functionalities to improve my performance and say I am killing two birds with one stone? Since I'm not transmitting over these symbols, my bit error rate is going in general to be improved. If my bit error rate before employing this algorithm was something like this, let's say this is the signal to noise ratio, and the y-axis is the bit error rate, and my bit error rate was something like this. After I use this technique and deactivate these subcarriers corresponding to these bad subchannels, I will get bit error rate closer to the y-axis, something like this, and you get gain of 5 dB. And I told you 5 dB or 6 dB, like 6 dB 4 times the power. You, instead of reaching a range, instead of allowing your signal to reach a range of 2 kilometers only, now you can reach 4 or 5. And this is significant improvement in your coverage, in your signal quality, in your data rate. Amazing improvement due to just understanding this basic concept. So I am already familiar with this, and when I got this, the point is channel polarization here, I say, man, this is not new, but in polar coding in polar coding field, this is something, yes, maybe new. Well, because codes have never been designed while considering the channel. So what does this say? Let's read together and we try to map this to the previous example that I gave about wireless channel. Here we talk about noisy channel, not exactly multipath rarely fading channel. The previous example was about wireless multipath fading channel. But at the end of the day, both are channels. So it says here, the channel polarization phenomenon. Let a binary input discrete memoryless symmetric channel with capacity, the capacity of this channel is between 0 and 1. Binary input is that you are allowed to transmit as input 0 or 1. Discrete memoryless, it doesn't have memory, means there is no dispersion, no multipath, and the capacity of such system is usually limited between 0 and 1. 1 means this is the maximum data rate you can achieve, 0 is the lowest, and your capacity is usually limited between these two. When a code word is transmitted in n-channel uses, what's the code word? Let's say this code word. You have code word of 0, 1, 1, 0, 1, 1, 0. Code word of zeros and ones, binary bits. The channel polarization, this phenomenon that was discovered in the coding field, they call it channel polarization. We call it in the wireless multipath, in the wireless domain, we call it like, we didn't name it such names, we usually name it good channels and bad channels. But what channel polarization says? It says that it converts C fractions of the n-bit channels as noiseless, and 1 minus C remaining as extremely noisy. What does this mean? You converted them, you classified them into noiseless, their capacity is equal 1. Whatever you transmit over these subchannels, you will get them right, you will not lose them, you will detect them correctly, and we call their capacity is 1 because they are noiseless, there is no noise. This is the first extreme. And the second one is what we call extremely noisy, which means you cannot recover your data successfully. Okay, remaining as extremely noisy. Now, this extremely noisy, the capacity is equal to 0. Now, what do you think this new term, new concept that we call channel polarization, how is that related to the previous phenomenon that I explained about wireless channel? Don't you think that it's relevant? They are almost the same. When I say noiseless, means they have good channels. You can transmit over them because whatever you transmit there, most probably you are going to receive. And when we say extremely noisy, means whatever you transmit here, you are not going to receive or be able to detect or correct because it's noisy. And this corresponds in our case to the bad channels, bad subchannels that we don't recommend transmitting over them because they degrade our performance. So when I discovered this new thing, I got into this domain. I got really motivated into this domain. I said, this is not very far from us. This is really, we already know this. We have been implementing this for wireless channels. We have already even contributed few papers in this phenomena, bad and good. We exploited it for peak to average power ratio, for out-of-band emission, for better rate enhancement, for noise enhancement reduction, for security purposes even. When you have good channel, you transmit over them. When you have bad channels, you don't transmit. And since the channel is decorrelated based on the position of the user, and these are optimized to the legitimate user only, the bad user will not be able to know what bad user will not be able to recover all the bits we transmit to the legitimate receiver. And this led me to the new topic, a new contribution, new paper that I will share with you called How to Design Polar Codes, Designing Effective Polar Codes for Multipath Wireless Channels. You know what I discovered in the literature? I found out that polar codes is only proposed for binary symmetric channel and additive wide Gaussian noise channel. And they have problems implementing it for multipath channels, for dispersive channels, for time selective. So I said, this is our expertise. This is what we always assume in our simulation. So let me now take polar codes, the polar codes that are designed to additive white Gaussian noise channel and make them work for multipath, frequency selective, time dispersive channel without doing any modification to the transmitter and to the encoder and decoder or the construction process. Because what I found in the literature, when the researchers tried to improve, to generalize polar codes to the other fading and channels, each time they propose it for a new channel, they had to redesign the construction process of the polar codes in such a way that it meets that channel characteristics. So what they ended up having so many different constructions for so many different channels. While in the design we proposed, we said, regardless of the channel, regardless of what you have, we have just one design that's applicable to all the other channels. You just use it. You just take the design that was used for additive white Gaussian noise, and by using our algorithm, you can just put it there and see how it works and function and give you close performance to the additive white Gaussian noise. And the way we do it, we just return back to this basic idea of good and bad, and we said we classify them to good and bad and we design an algorithm that can determine exactly the bad and good, and then use these codes, these good subchannels, to encode the data over them in such a way that you can achieve the Shannon capacity, and also without the need to redesign the polar codes again and again. And that was really very significant. We got really very significant improvement, and at least we now for the first time for the frequency selective multipath channels, which are the more practical ones, and with a simple design that you just take it and put it and use but the design is also kind of channel dependent. You need to have some information about the channel at the receiver. So at the end of the day, polar codes have been implemented not only for additive white Gaussian noise or binary symmetric channel. The research has been extended to cover all the several different types of channel with different coding instructions. But long story short, what drives this are the attractive features of polar codes, which are summarized as follows. First, it has fixed, low, and deterministic encoding and decoding complexity. Fixed, it's not random, it's not dependent on the channel behavior like the previous code did. And it's low complexity and deterministic. You know exactly how many flip-flops you are going to use, how many XORs you are going to use. So it's such an attractive encoding structure. Also, you have explicit construction, like step-by-step way, and easy to implement, low complexity, and does not cause too much delay, especially the encoder, although the decoding a little bit complex. But now, let's say someone might come and say, you are saying polar codes are the codes that are achieving the capacity of Shannon for the first time, but this is not very accurate. We read in so many papers that there are codes available and existing in the literatures that almost approached the capacity limit of Shannon that was defined by Shannon. So I tell you, yes, that's true. There are codes that were successfully able to achieve the Shannon capacity, where their performance was very close to the Shannon limit. But the problem there, these codes were not proven mathematically. They got them by simulation, and just simulation, you cannot regard it as a definite proof of your idea, of your method. You need to make sense out of it by math as well. And for good ideas to be accepted worldwide, you need to prove them not only by simulation, but also by math. And that's why polar codes got too much attention, and even more than the previous codes that were a little bit close to Shannon capacity, because it was proven mathematically. I mean, you are not playing here. It's the math says this, and you get it easily when you go to the simulation and practical implementation. So example of these codes, competitive codes that were able to achieve, for example, turbo coding that has been used till now in the wireless industry, especially in LTE networks. You get very close to the Shannon performance limit. Also advanced version of LDBC codes, which are used in Wi-Fi network. LDBC codes. There are advanced version of them that can be very close to Shannon limit and in terms of error performance and data rate. And there are also Reed Solomon codes and some others. They also very competitive. They really do very well as well. So here these are the main features, and here the channel polarization, how to deal with it. So you classify, you take one branch, you start from certain signal to noise ratio design, and you start dividing it into sub branches until you reach the number of branches that's equal to the code length. Let's say you have a code length of 16 bits, so you keep making branches from the main design SNR until you have 16 leaves, 16 line, 16 output point, and these you classify them into good and bad based on their values, the output value. The one that has larger value, you say it's good. The one that has lower value, you say it's bad. And then you use these values to determine the good ones. You use them for transmitting bits. You put the bits on top of them. You encode the bits on top of the good. And the bad ones, do you know what do you do with them? You freeze them. You don't transmit over them. You freeze them. But this is kind of not utilizing the channel effectively. Yes, you freeze them. You are not able to use them. But maybe this is a good research point we can exploit in the future, how to make use of these frozen bits, because they are not carrying anything, but we are using them. And after you determine these values, you use the encoder structure, which is XOR operation. You take the input bits and take the output, and then you send through the channel. And this is a simple example showing you over a binary symmetric and additive white Gaussian noise channel. So when we say memoryless channel, there is no multipath, there is no time dispersion, there is no frequency dispersion, no time selectivity, frequency selectivity. You are talking about simple basic wireless channel, which is like even additive white Gaussian noise channel. So when you have the bits, modulate them using a simple modulator, let's say like BBSK, and you transmit them over channel, additive white Gaussian noise. Then at the receiver you have match filter in order to improve the signal to noise ratio, then correlator, and then decision rule, which is maximum likelihood, or MAP, maximum a posteriori period. This is the probability, the maximum probability of your received signal. So now you have this channel. When you have the modulator BBSK and additive white Gaussian noise, you get an equivalent channel. We call it binary symmetric channel, where you have the input to the channel is 0 or 1 and the output is 0 or 1, but with different probabilities. The probability of sending 0 and receiving 1 has error probability, we call it P, and the probability of receiving it correctly, we call it 1 minus P, which is the probability of receiving your bit successfully, and the same for 1. So this whole system here is equivalent to this system, to binary symmetric channel. So when you have additive white Gaussian noise channel coupled with PBSK modulation, and you are using these blocks, so at the end of the day, what you see from this point and this point, you see this. All these blocks are as input they are taking bits, zeros and ones, and as outputs they are producing bits as well, zeros and ones. An equivalent binary symmetric channel, you have your data, your message bits, k bits. Then after the polar encoder, you have n bits. Then you use BPSK modulation. As you can see here, then you transmit them over the channel, and then you have a polar decoder, which we call it successive cancellation decoder. The list of parameters we care about is n, which is the length of the encoded vector encoded sequence, k is the information bit sequence, and EC is the energy of the bit, and N naught is the noise power. And you define the design SNR. The design SNR is basically the value that we use to construct the polar codes. We will show you how now. So here, the main advantages and versus the challenges that we have for polar codes. First of all, anybody tells you why do we use polar codes and why it's important and this and that. You tell him first because it's simple, encoding and decoding, very straightforward, deterministic, fixed, low complexity, and explicit construction, easy to implement, and high hardware efficiency. It doesn't consume too much power while you are encoding it, has the best available performance under advanced decoders. When you use sophisticated, powerful decoders, it can give you very good performance, and most importantly, it has no error floors in binary symmetric channel and binary erasure channel. Error floor means that this is what you get when you have error floor. The bit error rate is usually expected to reduce in value as you increase the signal to noise ratio. This is bit error rate. But unfortunately, when you have error floor problem, you increase the signal to noise ratio, but you never going to decrease the bit error rate below certain value. It saturates here. You remain here on this. And the reason for that is the type of encoding sometimes causing interference between the bits. And due to this, no matter what you improve, what you increase the signal to noise ratio, you get the same bit error rate. The challenge is it's first of all high latency. The latency dependent on the length of the code word. Poorer performance under successive cancellation detection when you use simple decoder at the receiver like successive cancellation detection, you cannot beat LDBC codes. So to beat LDBC codes, you need to use sophisticated decoders as the ones that LDBC codes use. So there are solutions, but always these solutions come at certain price in terms of complexity and latency. So these are the important points. Now we move to the construction of polar codes. How do we construct them? So in simple terms, the selection of k out of n indices is what we mostly use in polar codes. You need to determine the good indices and bad indices of the channel so that you use the good ones to encode over them, and the bad ones you freeze them, you put them zero, you don't transmit over them. This is what you want to know before you construct your code. While you are constructing your code, this is number one step. Many algorithms exist to do that. The simplest is to use the recursion For what's the algorithm that we use in wireless channel to determine whether it's good or bad? We estimate the channel at the transmitter and put certain threshold and say if it is below this threshold, it's bad. If it's above, it's good. But here we use different methods because in over an additive wide Gaussian noise channel, you cannot by no means you cannot assume you know the channel, the additive wide Gaussian channel at the transmitter, because you cannot learn it. So the channel at the additive wide Gaussian noise channel is random, and you cannot learn it by training sequences. You cannot estimate it at the transmitter side. So therefore, you cannot assume that you know the channel and determine the good and bad. What do? We use an algorithm that start from certain error probability bound, and this you divide it into, you use certain algorithms, certain formulas to divide this error probability into multiple other probabilities, and you keep dividing until you reach number of outputs equal to the number of bits inside the code word, and then you use these bits you use these values or indices to encode your data over them. So the channel here, additive wide Gaussian noise with zero mean and variance in 0/2, used for the purpose of illustration. So the following decision holds for any commonly used channel such as binary erasure channel, binary symmetric channel. So binary symmetric channel, we understood that this is the one we talk about when we say binary symmetric channel is this. Keep this in mind. And most of the talk in this lesson, this lecture, will be related to this one. We will not talk about the wireless multipath. I will share with you the document related to that. Maybe we can talk about it in the future, but for now we talk about this type of channels. So now let's now go here. What do you do to construct the codes to determine the indices that are good enough to transmit over them your data, and the indices that are so bad, and if you transmit over them you will lose your data, and that's why you freeze them. Basically, you determine you perform polarization here, and you try to find the noiseless channel and the noisy channels. Noisy, you don't transmit over it, and noiseless, you encode your data bits over it. The way to do it, you start from parameter, we call it Bhattacharya parameter for additive wide Gaussian noise. This is the parameter, and this basically gives you the error, the upper bound on the error probability performance over additive wide Gaussian noise channel. Okay, it's like bit error rate, the upper bound on the probability of error performance, and it's, as you can see, it's function of the SNR. As the SNR increases, the probability of error decreases. Okay, think of Z as the probability of error. Then using this method, you can divide it into, you can take two branches, divide this value into two other values based on these formulas. You take this value, take its square, you take this value to Z minus Z square, and each of these values you keep dividing them according to these two formulas until you reach n leaves here, n outputs, because based on the length of your code word, and then you find the values, the lowest values among these. Let's say you found your encoder for your encoder is taking only you encode your data over five sub-channels. You select the best 5 sub-channels here, the highest 5 values, and you say These are the ones I'm going to use for transmitting my data over, and the remaining ones you call them you output them as J. Find here in this step, you find the leaves holding K least values. Let their indices be J, you output J. Since they hold the least values, you don't use them for transmission, you freeze them. And the complement of J is I, and which is the information bits you encode over it. The problem here reduces to finding at what design SNR we should design the polar code. Yes, you tell me, okay, I can determine n, I can keep going backward until I reach the number of a tree has n leaves. N leaves indexed from top to 0 to n minus 1. I can do this, I can find the lowest values, I can output J, I can determine I, but what's this signal to noise ratio here? Which signal to noise ratio should I use? From where should I start? Yes? So the signal to noise ratio here, there are several studies on this issue, and I think that this design, the signal to noise ratio design here, EC over N naught, basically the question here, what signal to noise ratio you should consider as a starting point for your design. I can put EC any value. I can put N naught any value. Based on what? Can you tell me based on what? Based on the position of the user from the base station. Based on, since we assume, let's assume additive wide Gaussian noise channel, yes? And line of sight channel. There is no multiband, line of sight. Then based on the position of the user from the base station, you can determine the amount of path loss. Let's say you transmitted 10 dB, but due to path loss, you lost 5 dB, and now you have 4 dB left. So here the EC, you can say that the EC, the energy, is higher based on the location of this user is equal to 4, and the N naught is you determine it from the spectrum analyzer or from the measurement devices, and you say then this is the design SNR that I should start from for any user located at this position. If you don't do this, your design will not be optimized. Usually you might make a mistake. Consider this channel as good channel while it's not good, or consider it as bad while it's not bad. So here, these are the first step in construction of polar codes. Then we move to the... So here, a very important characteristic of polar codes, the non-universality. Why non-universality? Can you tell me why from the previous point I mentioned? Non-universality because it depends on the design SNR. For different design SNRs, you get different N values as good and bad, as noiseless and noisy. So code can change significantly with different choices of design SNR. Based on the design SNR, the construction code can change. And I told you, I gave you a brief intuition of which SNR you should use, which is most probably, it's gonna be related to the path loss in the channel and how far the user from the base station, because from the distance from the base station you can calculate the received power. The choice of a good design scenario is very important, very critical, and more accurate construction algorithm exists in many papers in the literature. The best achievable performance is approximately same for many construction algorithms, for at least until n less than or equal 64K. So mainly you have these issues while you are designing the construction code, but I gave you a hint how to get an idea how to design it. If I tell you the user is far from the base station by this distance, this means that this the EC has this value, then I should use this design SNR to start building my code because it will be optimized for that position. If the user gets closer or farther from the base station, then the design SNR changes, and I need to reconstruct the codes again. This is one of the key drawback of Polar codes. So how do you do the encoding systematically? You have n bits as which is the length of the code word. You have k information bits, and you have I, which is the indices of the noiseless channels, the ones you can transmit and encode your data bits over them. N is equal to power n code length in bits, k information length in bits, I is, you take it as the complement of j, this is MATLAB function bit reversed, a set of k indices where you transmit information bit indices, we call them. The complementary set is called frozen bits. This j, the complementary set, is frozen bits. And you use kernel. The kernel, think of it like the generator matrix in block coding. You remember in block coding how we used to find the code word v? V is equal to u multiplied by the generator matrix, or generator matrix multiplied by u. This is how you design your you design your encoded word, encoded vector or code word based on generator matrix for block codes. In Polar codes, we don't use G, we use something similar, but it's different a little bit, and we call it kernel. And this kernel contains only zeros and ones, and these zeros and ones are designed in such a way that they minimize the complexity in the construction circuit, in the circuit that builds the encoder. So let's see an example here. You have the example here. If your the number of bits in the code word is equal 8, which is this one related to the output, and k information bits 5, and the indices of the good noiseless channels are 1, 3, 5, 6, 7, then how do you find the code word, the encoded vector? X is equal to f kernel to kernel 3. Kernel of type 3 means you have each kernel has this value 0, 1, 1, 1, matrix of 4 bits. When you have kernel of 3, when you have kernel of 2, what do you do? Kernel of 2, it's like big 0 here, big F here, big F, big F. What's big 0 here? Big 0 here is 2 by 2 matrix of zeros. And F here is this. F here is this again. F here is this. So you end up having a matrix like this. You have a very big matrix has the following values. 1 in the first part here, 1, 1, 1, 0. Here 1, 1, 1, 0, 1, 1, 1, 0, and here 0, 0, 0, 0. For the case when you have three kernels, you get something like this. You get here 0, F, 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 and again you repeat it again. So you end up getting this. This part, the 0 part, this is the 0 part, and this part is F2, kernel F2, and this part kernel F2 also, and this part kernel F2. What's this kernel F2? Look at it. Let's change the color and let's look at it. It contains 0 part, and here kernel 1, which is 1, 1, 1, 0, kernel 1 again repeated, kernel 1 again repeated. This is how you build the matrix for any kernel. Even you can find kernel 10, kernel 3, kernel 5. In coding, in simulation, very easy to find it. You just determine the patterns and find it. but each kernel f is 0, 1, 1, 1. When you have kernel more of order more than 1, you need to put the kernel itself in the matrix. And then kernel 3, you need to put the previous kernel as the main component of the matrix. Yes? To explain it better, let's return back here. This, if I tell you find kernel 5, kernel 8, this is kernel 8. How do you find this? Kernel 8 is equal to, what do you put here? 0 matrix of, this is 1, 0 matrix here, and this f kernel 7, f kernel 7, f kernel 7. Now f kernel 7 is equal to 0 matrix here, f kernel 6, f kernel 6. You keep dividing it like this. You substitute this value, whole value, into this. And f kernel 7, there is another value for another matrix for it. It's sequential. You need to keep plugging the matrices inside of each other until you get the final matrix that I showed you here for the case where you have kernel 3. For example, kernel 3 matrix is this. Now you need to take the information bit sequence. The information bit sequence, the number of bits you transmit, 5. It's determined by the code. 5, yes? But you don't know where to put these 5 bits. But I give you I, or I tell you find I based on the temperature I value, and find the lowest, the points, the outputs corresponding to the lowest point, to the lowest values, and you say these are the indices that have to be frozen, and the complementary of them are the indices that I should use for transmitting my data. So I put my data bits like this: D1 over position 1, D3 position 3, D5 position 3, D6, and D7. And the other ones I don't see here 2. Sorry, this one D0. Let's just explain to you here. These are the indices. The indices usually start from 0 till n. Till n minus 1. What's n minus 1? 7. So at 0, it's not included in the set I. This means that it has to be frozen. So D0 is equal to 0. Here you put 0. D1, index 1, I have 1 bit, 1. You put it. Instead of D1, here, whatever the value of the bit, you put it, but you activate it first. And D2 here, index 2, do I have anything? It's not included in the set. 2 is not included in the set, that's why I put it 0. 3 is included, I put D3. 4 is not included, I set it to 0, and the remaining are appearing in the set, that's why I put them in the information sequence. Now, these are the indices. Now, let's say the information bits are something like this. What do? You just put these bits here. 0, you put it in D1. 1, you put it in D3. 0, you put it in D5. 1, you put it in D6. And last one, you put it in D7. And then you encode, you multiply it with the kernel. And as you can see, since you have some zeros here, the zeros, these columns will not contribute anything. You will get, your multiplication process will be deactivated at these positions, which reduces the complexity of your matrix generation. So to simplify it and make sure that you understand it properly, always compare it with the case of block coding. for the 3 lectures that I shared with you before on convolutional codes and block codes. The code word is equal to G multiplied by U, where U is the information sequence and G is the generator matrix. And here in polar codes, instead of U we have D, and instead of G we have kernel matrix of power n, and X is the code word or encoded sequence. And here the complementary of I, the indices of complementary of I, you put them to 0, and the indices of the I, you use them to put the information bits on them, as I showed you just right now. So this is now you know how to encode. Then it's straightforward. You know, this is by math. This is by for the sake of getting the bits. But now let's say you want to encode using a circuit. You build the circuit that you can use to encode. So the circuit is basically you can build it from the kernel. Here you have the output here. You put the output, and you have the input, and you determine the frozen bits. Where are they? And the circuit here is XOR circuit of kernels. For example, this is the first kernel. This is another kernel, because this like if this is something like 1 1 1 0 1 1 1 0. So you have lower branch, upper branch, and you have 3 stages because you have kernel 3. And by using this circuit, this circuit represents this matrix. And by using this XOR circuit, you can just find the output of any input information sequence. The decoding now, the decoding process. The basic decoder we use for polar codes. Now we understood how to encode the information bits using polar codes, how to construct the codes, how to determine the indices of the subchannels we will use for transmitting our bits, and how to choose the design SNR. Now we need to transmitted the data over the noisy channel, and we received the sequence, the encoded sequence. We want to decode it back to the information. The basic decoder we use is successive cancellation decoding. Is also fundamental to more advanced and efficient decoders. The key feature of this encoder is its low complexity. This is why we like it. Is also fundamental to more advanced and efficient decoder, very efficient, uses another two-way recursive algorithm. You remember with me the decoder we used with NOMA in the previous lectures related to 5G cars. We explained to you how to use successive cancellation detection. You detect the first and then you subtract it. This is kind of similar to it, but applied and implemented on the bit level, not on the symbol level. Uses another two-way recursive algorithm on n received likelihood, obtains n new likelihoods in n iteration. So you need to produce likelihoods of the elements in X, as you can see here. So you received this is your received data. What you do, this is your received noisy elements, noisy bits L1 and L2. You take them to kernel F, and the output here you calculate F function. Its function, F is a function, it has certain formula. The input to that function L1 and L2, once you put the value of L1 and L2 inside this function, gives you value V, and this value influences the value at G. So G is also another function that takes L1 and L2 as an input and is influenced by F as well and gives you another value. So from the two likelihood operation in use, L1, L2 are now being transferred to F and G, and the functions are this. The function f is this. You take L1 multiplied by L2 plus 1 over L1 plus L2. This is like the first likelihood from branch 1. The second one is L2 multiplied by L1 or L2 over L1, and when you can use the second operation depends on the intermediate bit decision from the upper branch. So this is how it influences it. And once you get the likelihood here, numerical underflows are natural with using log likelihood operation. The new formulas become, to simplify the formulas, you use len. If you have, so these are the simplified ones, but basically you get them from other formulas that you, at the end of, after, like when you receive your bits, your values are carrying with them, yes, your received bits are carrying the influence and the effect of the channel. What's the effect of the channel? The channel is usually Gaussian, yes? And what's the main function in the Gaussian distribution? It's exponential, yes? So exponential is very hard to deal with if you don't convert it to logarithmic scale. When you convert to logarithmic, the len cancels the exponential. So that's why at the end of the day you get simple formulas like this. But initially you need to get them from the Gaussian distribution. So this is how the encoding, the decoding process. So the decoding process carries as follows. So you receive n input likelihood, n iteration, and n computational tree, different active depths. So this is how, when you receive your data, the the one in orange is the f function, and the one in blue is the g function, and the others are inactive. So based on the incoming information bits and likelihoods you calculate, certain branches are activated in the circuit, and you keep passing over this. This is like a program. It's encode. You just write it once, determine the values, and make it run for all the rest of the values. So, but the basic thing here that you need to know, that you need to calculate the likelihood operation, that because based on that you can determine the path, and you need to do this sequentially until you finish all the bits. These entries are naturally embedded in an n multiplied by n plus 1 array, which is shown next here. So here you have your bits coming from this direction and the log likelihood operation. And this is really the most difficult part of polar codes, which is the decoding process. But since we are using the kernel functionality, and kernel uses